Hi everyone, in today's video we're going to talk about vision transformers. We'll try to code them using JAX and flax, using the architecture provided by Scenic library. So let's get started. Before I talk about vision transformers, I want to talk about an error that I couldn't solve for 2 days. So I was importing the CFAR10 dataset using torchvision. Here. I'm using the torchvision and I'm using the transforms in torchvision, and one of the transforms is called toTensor. So when I load the dataset into the model, it throws an error saying that there is a dimension mismatch. And I couldn't figure out which function flipped the dimension, because I verified that the dimensions are correct. The channel is the last dimension. But it kept persisting, it kept throwing this error, and I couldn't figure out. Then I literally put a print statement after each line of code. And it turns out to be the problem is coming from toTensor function in torchvision. It takes a PIL image from the CFAR10 dataset, which is height by width by channel, and it's in range between 0 to 255. What the name indicates toTensor, it's only transforming image to torch-tensor. It's doing that, and it flips the dimension. It brings the channel dimension to the beginning. So it produces a tensor with size channel by height by width, and it also changes the range of the array, and it normalizes it. Basically, it normalizes the values between 0 and 1. So this was my problem. So just a heads up, if you're using torchvision with JAX, make sure that you don't use toTensor, because JAX requires the channel to be the last dimension, and toTensor brings the channel to be the first dimension. And I just want to start with this advice, because I spent 2 days just trying to figure out what's wrong, which function is swapping dimension, and it turns out that it is this function. So here is the start of the code. First, I would like to acknowledge the help of these 3 references. I borrowed the ViT architecture from Scenic library, which is a library recently published by Google Research. It has all the architecture for computer vision tasks, for image classification, for object detection. I recommend that you check it out. And I also borrowed the CFAR10 pre-processing code from this GitHub repository, because I want to avoid using the toTensor function. And also borrowed some code snippets from this deep learning tutorial by University of Amsterdam. This is a very excellent course. I strongly recommend that you go through it. Here are some references. The reference for Scenic library, a JAX library for computer vision research and beyond. And here is the original reference for vision transformer. An image is worth 16 by 16 words transformers for image recognition at scale. I'm importing Scenic and importing the libraries. I like the notebook to be self-contained, so I brought the architecture classes to the notebook, and I kept the imports to the minimum just to make the notebook self-contained. I'm setting the hyperparameters. I'll get back to those once we need them. The first class is the add position embedding. And this notebook has 4 classes in total. The first class is add positional embedding. Second one is encoder 1D block. The third one called class encoder. And the fourth one is class ViT. Just to have an idea about how these classes work together, let's go back to the paper, the original paper for vision transformer. And if we look at this figure here, so this figure is very excellent. It's basically explains the workflow for the vision transformer. So an image is cut into patches and passed through linear projection, and then to a transformer encoder. A transformer encoder has multiple layers. These are the layers inside the transformer encoder, and it has multiple heads. After finishing from the transformer encoder, the images will pass through a multi-layer perceptron head, and the classes will be determined. So I have my notes on this image here. The transformer encoder is basically class encoder, and a single layer of the class encoder is the encoder 1D block. Here is the ViT, which is the main class. It calls encoder here, just to get the encoder output. And if we look into the encoder class here, it calls for the number of layers, it calls encoder 1D block. So encoder 1D block is one layer of the encoder. So this is how these classes are organized according to the paper. So now let's break this figure down. Let's break it down and look at how the data flows inside the vision transformer. So if we pass an input to the class ViT, we give it all these parameters. The first thing, it applies a convolutional layer. They have a very good note here. Extracting patches and then embedding is in fact a single convolution. So this is what basically happened here. We have a batch size of 128 images. We're talking about CFAR10 dataset. Each image is 32 by 32 by 3. These are the RGB, these are color images, and this is the RGB channels. If we specify the patch to be 4 by 4, then we will have 8 patches along the height of the image and 8 patches along the width of the image. So we are applying convolution with 16 filters. 16 is a parameter. So we will end up with 8 height, 8 width, and 16 depth, 16 filters for each image in the batch. So that's why we are using convolution layer here. Then we are extracting from the X. X is the input. N is the batch dimension. H is the height of the image after applying the convolution. W is the width of the image after applying the convolution. And C is the filter, the size of the filter, so which is in our case is 60. Then we are reshaping the image by just flattening the height and width. So instead of 4-dimensional array, we end up with the 3-dimensional array. This is what happened here. So instead of having 128 by 8 by 8 by 16, we will flatten these 2 dimensions, the height and width of the images, to be 64. 8 times 8. We will end up with a 3-dimensional array of size 128 by 64 by 16. If we choose the classifier to be token classifier, we will add a class token. A class token will be concatenated to the images. So instead of 64, we will end up with 65. So after adding the class token, our 3-dimensional array will be of size 128, 65 by 16. Then after that, we will call the class encoder. The class encoder basically will pass X through the number of layers. The number of layers, we set it to be 6. And for each of these layers, it will call the class encoder 1D block. Inside the class encoder 1D block, first X will be the inputs after applying the layer norm. Then X will be passed through multi-head dot product attention, then a dropout, then a stochastic depth, then it will be added to the input. This attention block here is equivalent to the figure in the paper, this part here. So this is the input. X will be the input after applying the layer norm. It will be passed through multi-head attention, then it will be added to the input. So X equals X plus the input. So this is the attention block. The next step is the multi-layer perceptron block. So Y will be X after applying the layer norm. Then Y will be passed through a linear layer, which is a dense layer in flax, non-linearity, which is specified here by GLO function, and then after that another dense layer. Then at the end it will apply stochastic depth. The output will be the output of this class encoder 1D block will be Y plus X. So this MLP block is equivalent in the paper to the to this part here. So y will be x after applying the layer norm. It will be passed through multi-layer perceptron and it will be added. So y plus x. And this is the output of a single layer in the transformer encoder. Note that we are calling that 6 times because we are specifying the number of layers to be 6. Here is another way to visualize it. The input is 128 by 65 after adding the class token by 16. In the attention block, x will be the input after applying the layer norm. It will pass it through multi-head attention, drop out, then it will be added to the input. Y, which is in the MLP block, will be x after applying the layer norm. It will pass through a dense layer, a linear layer, then some non-linearity, then another dense layer to get the output. The output has the same size as the input. Now we download CFAR10 dataset. These are two helper functions. The first one is image to NumPy and the second one is NumPy collate. We will get back to those in a second. So the classes, it has 10 classes. And the test transform is only image to NumPy. So for the test images, we are only converting them to NumPy arrays. But for the train transform, we are performing random flipping and random cropping. This is called data augmentation before we train the model, just to increase the diversity of the data set. And then after that, we are converting them to NumPy array. Remember, don't use the function to tensor, because that will flip the dimension of the channel dimension. It will bring it to the front, and it also normalizes the image between 0 and 1. So here we're calling torchvision.dataset.cfar10. We are calling the train split by setting train to true, and we are specifying the transform to the train transform. And the test set, we're importing the test set by setting the train to false. And for the train loader, we are setting the batch size to the batch size which we specified earlier to 128. We're setting shuffle to true, and we're dropping the last batch because the last batch might not have 128 samples exactly, so we are dropping that. And we're setting collate function to be NumPy collate. So image to NumPy, basically it converts the image into a NumPy array of type float32, and it normalizes the values between the data means and data standard deviation that we specified earlier for each channel. So if you go back here to the hyperparameters here, so this is the mean for each of the 3 channels, and this is the standard deviation for each of the 3 channels. NumPy collate function, we call it here, instead of using the default option, which is torch tensors, we are converting the images into NumPy arrays here. So here I'm checking the length of the train set, the length of the train loader. The length of the train set is 45,000. The number of batches is 351. So if we divide the number of samples by the batch size, we will end up with 351. But we ended up with the 351 batches, and we dropped the last batch. In the train set, the number of samples is 10,000, and the train loader has 79 batches. If we divide 10,000 by 128, we will end up with a 78.1. So the 0.1 make the last batch, which is not exactly 128 samples. Here we're checking the size of the first batch. We're also checking the data type. We want to make sure that the data types are the float 64, not torch, not float 64, just to make it compatible with JAX. And here we're initializing the model with the number of classes, which is 10. The MLP dimension, which is 256. We're specifying the number of layers to be 6, the number of heads to be 8, and we choose the position embedding to be learned 1D. And the patch will be 4 by 4 pixels. And here we specify the classifier to be token classifier. Here we're setting the optimizer to be Atom, and we're initializing the model randomly using this n-dimensional array, which is created randomly just to initialize the model. And we're creating the model state, which is required by flax to train the model. In the calculate loss, we are passing the batch, which is made of data and labels. We are getting the logits by passing the parameters and the data to the state apply function. And we're getting the prediction labels by taking the maximum element across each row of the logits. So this gives us the prediction labels. We are setting the one-hot label for the cross entropy loss between the logits and the one-hot label, and we're retaining the mean loss and mean accuracy. These three cells are for the training, but let's start from this one here. We are passing the model state that we initialize. We are passing the train loader, and we're setting the number of epochs to be 100. I could not go beyond 100 because Google Colab will kick me out. I'm on the free quota. So this will call train model function. Train model will run through the epochs and will run through the batches, and after finishing each epoch, it will compute the loss and the accuracy and print these out. The train step specifies the gradient function. It will compute the loss and accuracy from the function, calculate loss and accuracy, and it will return the grads as well, and it will apply the grads to the state. After training the model for 100 epochs, we're getting the accuracy of 92%. The testing, we are not calling the train step function, we are directly calling the calculate loss accuracy by passing the trained model state that we obtained after training, and the trained model state parameters, and the batch which comes from the test data loader. By testing the CIFAR10 dataset, we're getting 67%. Here in the confusion matrix, I know I'm looping over the test loader again, but I couldn't think of other way to do it, because I want the predictions and the true labels, the predicted labels and the true labels, and the calculate loss function only retains the loss and the accuracy. So I got the trained model, I got the logits, then I got the prediction labels, and I store the labels, the true labels, and I store the prediction labels in two lists. Then I'm looping over these lists just to and concatenating just to make a one-dimensional NumPy array for plotting the confusion matrix. Here I'm calling the confusion matrix display from prediction. I'm passing the true labels, the predicted labels, and I'm specifying the display labels to be the classes list, which has the strings of the classes, and I'm specifying the axis to be this axis here that initialized of size 8 by 8. So here's the final confusion matrix after training the CIFAR10 dataset on a vision transformer. I think you can increase the accuracy by increasing the size of MLP and running for more than 100 epochs. Yeah, I think that will increase the accuracy. My final remarks on coding vision transformer using JAX and flax. I found the compatibility with torchvision is very convenient, and it was great of JAX just to provide the compatibility with torchvision. But be careful, if you're using torchvision with JAX, be careful not to use to tensor function, because that will mess up the dimension and it will normalize the images to values that you might not want to. But overall, torchvision is a very powerful library, and it provides very large number of datasets that you can use both on PyTorch or JAX. About Scenic library, I found it very detailed and very documented, and the implementation in Scenic library has more comments than the implementation in Vision Transformer. So Google Research have 2 GitHub repositories that use Vision Transformer, but in a Vision Transformer GitHub repository, the code was not documented as good as in Scenic library. The Scenic library, I could follow the code and I could see the comments that are useful and very detailed and informative. That's it guys for today's video. If you find this video helpful, please like and subscribe. By the way, you can find the link to the notebook I'm working on in the description below. Thanks for watching. Bye.